So, the problem is that we have a graph and we want to get from node A to node B so that the sum of edges on our way is the smallest. And this is pretty common problem. For example, Google Maps are computing shortest path all the time. So how do they do it? Well, I don't know what algorithm they use in Google for this task, but mostly it's used Dijkstra algorithm. So let's see how it works. I got here an unoriented graph, so think of it as a road network. And I want to get from A to G so that the road's value is smallest. So if you think about it, you can just try out all the options, but that would be really inefficient. Imagine that you have the road network of all United States, and if you want to try all the possible paths, you will wait for the result forever. So what Dijkstra's algorithm does is it takes also kind of brute force approach, but it does that more smartly because it goes through the fast roads first. So let me show you how it actually works. We are starting in A, and we also have a priority queue of nodes where we keep track of how much time it takes to get to a particular node. And at the beginning, all nodes have infinity because we haven't got to any of those nodes yet. And what Dijkstra does? Well, it takes a look at where we can get from current node and then change the value of path to that particular node and puts these nodes back to priority queue. And I forgot to mention this, in the priority queue, all the nodes are sorted based on how much time it takes to get there. So let me show you how it works on an example. I think you will understand it better there. Here is my graph, and here is my priority queue, and I'm going to take the first node from priority queue and check where I can go. So in this case, I take A and see that I can go to B and it takes me 5. So I will change value of B in priority queue and also set the node from which I got here, and that is A. I can also go to C and it takes me 2, so I will change the value of C from infinity to 2, and I will also move C above B in priority queue because this priority queue is sorted. This is actually an important step because then we are always taking first node from priority queue, and that is why we are looking at faster path first. But anyway, I also set the node from which I got to C to A, and look at last node, and that is D. So D have value of 7, and I got here from A. So now I have gone through every edge from A. So I can delete A from priority queue and grab the first node in priority queue and do this all over again. So from C, I can go back to A, but since that is where I got to C, it is useless to go in there again, right? So I will skip A. From C, I can also get to D, and this edge have value of 2. So I take a look at how much time it takes to get to D now, and if the value is bigger than the sum of path from start to current node and the edge from current node to D, I change the value. So in this case, I add up 2 because it takes me 2 to get from A to C, and then I add 2 because it takes me 2 to get from C to D. And that gives me 4. And current shortest path to D is 7. So I will change the value to 4, and I will also change the node from which I got here to C. And I also need to get D up in priority queue because it has smaller value than B, right? So now I look at other edges from C. So I can get to E, and it takes me 2 plus 7. So I changed the value of E to 9, and I got here from C. And these are all the edges that leads from C. So C is done, and I can delete it from priority queue. Now I grab D from priority queue and see where I can get from D. And I can go only to F, and that takes me 4. So I will add up the value of D with 4 and set it as a new value of F because 8 is smaller than infinity. And I also set the node from which I got here to D. I delete D from priority queue and I grab B from priority queue and see where I can get from B. I can get from B to E and it takes me only 2. So I add up value of B with 2 and get 7, and I can see that E have value of 9. So I change it to 7, and I also change the node from which I got here to B. Now I delete node B from priority queue and grab node E, and I can get from E to F, and it takes me 3. So I check whether the add up value, so value of E plus 3, is smaller than the current value, and it is not. So I leave it and move on to next edge. And this edge takes me from E to G, and it takes me also 3. So the path to G takes me 7 plus 3, and that is 10. So I change the value of G to 10. And I also set the node from which I got here to E. But even though I reached the finish, I still need to check all the nodes above G in priority queue. So I delete E from priority queue and move on to F. Why do I have to do this? Well, imagine that there is edge from F to G and it takes only 1. Then the shortest path would be different, right? So I need to check all the nodes in front of G in priority queue. So from F, I can get to H in 4. So I change the value of H to 12 and I set the node from which I got here to F. And I can also get to G and it takes me 3. So I change the value of G to 11 and set the node to F. And remove F from priority queue. And as you can see, now G is first in priority queue. So that means I found the shortest path. So now I can reconstruct this path by looking at the nodes that I visit. So I got to G from E. I got to E from B. And I got to B from A. And that is our shortest path. I hope this makes sense, and I think it should, because it is still pretty much brute force algorithm. It doesn't go through the paths in proper direction. So Dijkstra's algorithm is kind of the core, but since it is still pretty inefficient, most of the used algorithms have some improvements, like they search roads in some direction. But anyway, that is pretty much it for this lecture. If you have any questions, feel free to contact me. I will be here to help, and I will see you next time.